All right, so here is a second example for class 14. This is a much longer example where we're going to run through this in 3 different ways. Now, of course, you don't have to use all 3 methods, but I think it's a good skill set to have. So this is from my book that's coming out soon, the Engineering Dynamics Course Companion. So what we want to find is we're looking for the velocity of C, given that we know velocity of B is going 1.5 feet per second downwards. And we also know that both the rollers at A and the rollers at B, they stay in contact with their surfaces, right? So you can picture this thing moving, right? That it's going to start to move over in this direction, but it's also going to be rotating as it does that in order to stay in contact. So hopefully you can picture what those are. So I'm going to go ahead and do this by vectors without writing out the diagram. So this would be like, let's call it the most traditional or most fundamental. And here is a typical dynamics dilemma. If we just attack the problem and look for the velocity at C right away, just to try to apply an equation, like what equation do I use for this? Well, basically the equation that we're going to eventually use to find the velocity of C, we would find that by using the known one that we have, velocity of B, and adding the velocity of C with respect to B. We will eventually need that. But if we started going down that path, we're going to find that we don't know the angular velocity. So if we were starting to go down that path, it would be just like going down the maze and finding a dead end. We'd have to backtrack and then find another way. So the other piece of information that we have available to us is that A stays in contact with the horizontal surface. So we use the thought process, and this is very typical, that like, okay, here's things that we know. If from that, we might be able to jump ahead if we have some experience solving problems like this and recognize that we can get the rotation, we can get the angular velocity. But we might not know that. We could just go ahead and proceed on some faith that, I think maybe I can get the information that I need to know by getting the angular velocity, and get the angular velocity by focusing on A and B. So let's try to find the velocity of A. It's actually something we don't need to know. We're doing this only as a means to try to find the angular velocity. So we write out the equation for the velocity of A using the thing that we know, the velocity of B. And we know that it's actually going to be the thing that we're going to need is that omega, and I decided to call it ABC, so I'm going to keep that up here. Let's see, that was really written poorly. ABC crossed against R, and that's going to be A with respect to B. All right, so I want to populate that. So over to the side, I'm going to write down the things that I know. I know that the velocity of A is going to look like velocity of A times I, right? We know that it's completely in the I direction. So I say it's the speed times I, because the VA right here without a hat is the speed. We know, and I'll keep this without numbers. I'll stick this. I'll put the numbers in later. So the velocity of B, we know that's negative VB, the speed J, right there. We don't necessarily know the direction, but we could actually figure it out on our own by observation that this has to be counterclockwise. I mean, it has to be clockwise. So it's going to be a negative number we're anticipating. We could leave that as positive and just find it out later. And we know it's going about K. And then we also, we could find the position vector of A with respect to B is going to be equal to negative LAB times the cosine of theta, I, and then plus LAB sine theta, J, right? Because we're coming from B and we're going to A, so we're going in the negative X direction and we're going upward, so it's the positive Y direction. And it's got that weird little thingy that jumps out for some reason. So we could go ahead and plug that in, and we'll go over here to the left a little bit further and write out my vector equations. Just plug all of these things in here. Negative VB J, and then minus omega ABC K crossed with, and I guess I'll put it in brackets, negative LAB cosine theta I plus LAB sine theta J. I barely got it to fit into that line without running into the other side. And I'm going through excruciatingly detail here to make the thing. So when I'm not skipping steps, what I'm saying, right? So I often do that when I'm writing things out. But for myself, maybe I would find some of those steps. So we combine this negative omega ABC with the negative LAB cosine right here, and we know that we're going to have positive LAB, and write out the cosine of theta, and that's going to be K crossed with I. Right, and then I'm going to drop down just a little bit here so I don't run into that position vector that's hanging out on the side. And then I have that negative omega ABC times my LAB, so that's going to be a negative omega ABC LAB sine theta, and then K crossed with J. All right, let's switch some colors here. I'll go blue. We want to take a look and see what that cross is going to do. I'll draw the thing up here. I do this to help myself out. I don't trust my memory, and doing it without some visual aid will mess me up. So I cross K into I, and I get positive J. And then I cross K into J, which I think we just did a minute ago, right? And we notice that our thumb points in the negative I direction, right? So grouping these all together, rewriting it out again, a little unnecessary. We get plus omega ABC LAB cosine theta J minus, well, actually it's plus because there's a minus right there, right? So plus omega ABC LAB sine of theta I. Now we can take a look at the I terms right here and set them all equal to each other if we wanted to. And we get VA is equal to omega ABC LAB sine of theta, right? That doesn't help us because we don't know omega ABC. But now we could go to the J, and we could say, oh, it's going to be 0 equals VB, something that we know right here. Double checking my answers here, my numbers. Okay, yeah. Okay, so yeah, that's going to be that should have always been negative right there. I left off that negative at some point. Minus right there, right? So that should be minus. Okay, so I was wondering why that was happening. And then plus omega ABC LAB cosine of theta, right here. And what we could plug in numbers for this because we know everything here. So just plugging in some numbers, we have negative, what do we say? It's 1.5 plus omega ABC times our LAB, which was 4 feet, right? There's 4 feet. And that way that's 6 feet. And that times the cosine of 25 degrees. We plug those numbers in and we're able to find omega ABC is going to be 0.4138 radians per second. Okay, that's all well and good. We can use that if we wanted to come back up. And if a lot of times a simpler question, we might have been asked, find VA. If that was the case, then we could have just gone back up to here and plugged in what we knew, 0.4138 times the length right there, which is 4 times the sine of 25, and we would have found that it's 0.6995 feet per second. And we might want to remind ourselves of the direction, right? Because that would be that direction. And down here for the omega ABC, we found that it was positive here because we already assumed it was negative based on arrangement. But the question is asking for the velocity of C. So now we rewrite this equation right here onto the next page. And so the velocity of C, velocity of C is equal to the velocity of B. And by the way, we can actually use the velocity of A here in this spot and be able to get out the same answer here because we do know the velocity of A now. But just for convenience, it might be to take the velocity of B. So we take velocity of C with respect to B added to the velocity. And by the way, we could have just went ahead and written the velocity, the angular velocity crossed to R C with respect to B right away. And looking at this, we're going to need to know what each of these pieces are. We already had the velocity of B. I guess I'm writing it again anyway. Is negative velocity of negative speed J, and velocity, the angular velocity we were given is negative. I could just stick numbers in here. I don't know why. On my paper, I've written it out a long ways again. Of course, for that, I'm just copying and pasting. But anyway, let's see. Maybe I'll shorten this down by sticking. No, I'll continue with the way I have it. You could just fast forward through there if it's getting tedious, and it probably is. Omega A B C K hat. I'm gonna get rid of that stupid thing. And then we also need to know the RC with respect to B. That's going to be a little bit different this time, looking back at the thing, because we're coming down. It's going to be a positive I, so it could be positive LBC times, I guess the cosine of theta, right? And then, but it's going to be negative LBC times the sine of theta for the J. So that's L BC times the cosine of theta I minus LBC sine theta J. All right. And we should also point out that we don't know the specifics. Velocity of C is going to is not going to be only in the I or the J direction. So we could write out also, and maybe this would be better if I had left myself some more room. Velocity of C is going to be the velocity of C x component I plus velocity of c, y component j. And so I'm putting these subscripts on the outside. These are the components that make up that full velocity. So if I write out that VC x I plus VC y j is going to be equal to negative VB j, and we know we need to distribute this thing right here. So we go, but that's going to be negative omega ABC K crossed with, and then in parentheses, this whole thing, LBC cosine theta I minus LBC sine theta J. Right, and then, really, do we have to do this? I guess so. Already started down this road. Maybe I'll make this into 3 different videos. So we'll do this example in 3 parts, because this video is going to be too long otherwise. Long videos suck. All right. So we go minus omega ABC times LBC cosine of theta, and that's going to be K crossed with I, right? And then it's negative, so it's going to be plus omega ABC LBC sine theta, and then once again K crossed J. So I'll switch up the colors here, go red. We find that K crossed into I is positive J, K crossed into J is negative I. So rewriting, do we have to rewrite? No, let's just group this. Let's just group the things together, right? So let's go in the I direction. We end up finding VCX is equal to negative omega ABC LBC sine of theta, and that's it right there, right? Because that negative, that's in the I direction right there. So we could actually just plug those numbers in there and say that we have 0.4138 that we were able to get from the first part of it, times 6, that's LBC, times sine of 25, and we get a negative 1.049 feet per second. And in the J direction, VCY, we get negative VB and negative omega ABC LBC cosine of theta, and therefore we get negative 1.5, that was a given, minus our 0.4138, and sine of 25. And that gives a numeric value of negative 3.75 feet per second. So the answer, VC, is negative 1.049 I plus negative 3.750 J feet per second. But more often than not, we want the magnitude and the direction of the thing. So we find the square root of the sum of the squares of VC. We find that to be 3.8 0.94 feet per second. And if we want to get the angle, I don't like to use theta for this. I did on my page here because we used theta originally for the other thing. So sometimes I will write this right here. Maybe I'll put a C or something in there, or we call it beta or some other Greek letter. But we were taking the inverse tangent of the vertical component over the horizontal component, and we don't necessarily want to play with the negative signs. We know it's going to be in that lower left-hand quadrant because it's negative and negative. So we just take our 3.75 and divide by our 1.049, and we end up with a 74.37 degrees. So the answer as a vector is 3.894 feet per second at, and I like to put, sometimes I went ahead and put the quadrant first. Sometimes I'll put this first here at 37 degrees right here. Okay, so that's the answer using the classic vector math, something that you should be able to do, but there's other techniques, and we'll do that in another example. So let's see, we can keep it, doesn't matter. And let's see how long the video was. 20 minutes long. That's a long video. Okay, well, we'll make the other ones soon. Okay.